So tangent to polar curves okay. Recall parametric curves. In parametric curves we have dy dx, if you recall, in terms of the parameter t, we end up having dy dt in the numerator and then dx dt in the denominator. Since the relationship between parametric and polar are such very close to, we can say that similarly replace the parameter t with a parameter theta, we end up having for the polar curve, we end up having dy dx equals dy d theta over dx d theta, like so. So we are at this point, which we use the same definition that we had for parametric curves, applied it to the polar. Where is the difference? Well, the difference is the conversion. In polar, first of all, by definition, in polar coordinates, or I'm sorry, coordinates would be the wrong word. In polar curves, we have r is a function of theta, as we saw last time. So, and we have also the conversion. And the conversion was, we converted x, we wrote it as r cosine theta, and y was r sine theta. Okay? So, when we take the derivative dy d theta and dx d theta, we need to keep in mind that r now is a function of theta. Might as well write it as f of theta for r times cosine theta and f of theta for r times sine theta. And it becomes clear that we need to use the product rule when we differentiate x and y with respect to theta. Okay? So, so let's differentiate x and y with respect to theta. So let's see, what is dx d theta? Well, dx d theta, by the product rule, it will be dr d theta times cosine theta plus, and actually it will be minus, because we have r times negative sine theta. So we end up having dr d theta cosine theta minus r sine theta. Okay. Likewise, dy d theta will be dr d theta times sine theta plus r, and the derivative of the sine is the cosine. Okay. So putting these together up here, we end up having the following expression, dy dx. Instead of dy d theta, I'll take what I have here, and I have dr d theta sine theta plus r cosine theta. And instead of dx d theta, I have this expression, dr d theta cosine theta minus r sine theta. So this is the end result, and I kind of jumped last time, and I just gave you the expression in the box. It said, okay, this is the first derivative. What this relate to the tangent? As we know that the derivative of the curve will be the slope of the tangent. So this is the slope of the tangent to the polar curve. Now, kind of, there is a little bit of ambiguity here, because, not ambiguity, actually, that won't be the right word, but we're talking about the polar curve, we're looking at dy dx. So obviously, everything will be expressed in terms of r and theta, rather than dy and dx. But the overall, I mean, the polar curve, we can go ahead and replace it on a Cartesian system, putting the pole at the origin, and the slope to the curve at any given point will be this expression, dy dx. Okay, so having said that, let's look at a special case. Well, before we move on, let's talk about horizontal tangent and vertical tangent, because we're gonna look into these cases. Well, the horizontal tangent required that dy dx equals 0, right? And the vertical tangent required that either dx dy equals 0 or dy dx is undefined. We need division by 0. So let's write that for horizontal tangent, okay, if I'm looking at this expression right here on top, okay, I want the numerator to equal 0, so this requires dy d theta, the numerator, to equal 0. On the other hand, for vertical tangent, we want the denominator to equal 0, so we want dx d theta to equal 0. So keep that in mind. Okay, and another special case is what happens if r equals 0. Okay, actually, I need to go and bring it back here. If r equals 0, at the point where, you know, in many cases, there is a place where r equals 0, what will be the slope of the tangent at this point? Well, if I'm looking at this expression in the box, if r equals 0, well, it doesn't mean that the r d theta equals 0. If the r d theta is not equal to 0 and r equals 0, first of all, r cosine and r sine go away. And then what you have is the r d theta divided by itself, and then you have sine theta over cosine theta. So, at the pole, remember the pole is where r equals 0, we have the y dx, okay, becomes the r d theta times sine theta over the r d theta cosine theta. And if dr d theta is not equal to 0, well, we need that to have, then we end up having tangent theta. Just like that. Everything at the pole when r equals 0, then we have simply tangent theta for the slope of the tangent. Here we need to be careful, so we need to write if dr d theta is not equal to 0. Otherwise, that it won't work. So also, when we're talking about the horizontal tangent, we need also add a little condition here. Again, let me bring the previous page before. Let's the previous page side by side. Let's look at this again. The box on top. Okay. If we want to have horizontal tangent, we want the numerator to equal 0, but we don't want the denominator to equal 0. And vice versa. If we want a vertical tangent, we want to have dx d theta equals 0, but we don't want 0 divided by 0 because it's undefined. So we want dy d theta to not equal 0. So here we need to add two conditions. Okay, in parentheses, this is if dx d theta is not equal 0, then we have a horizontal tangent. So we have dy d theta equals 0, but dx d theta is not. And likewise, vertical tangent, we need to have if dx d theta equals 0, but dy d theta shouldn't equal 0. And we'll see an example where this happened when we have both equal 0, and we see what to do in this case. Okay, but keep that in mind. So we have condition all over the place, including where r equals 0. We still require that the r d theta to not equal 0. And the following example demonstrate a little bit of that. Let's look at, I'm talking about r equals 0. Let's recall the four leaf rows. Okay, we did it last time. The four leaf rows was r equal cosine of 2 theta. Okay, and it looks like that. The four leaf rows, we started at the polar axis. This is the pole. This is the polar axis where theta equals 0. Okay, and if, let's see, how did we go? Did we went down or up? We went up first, right? We went up like so, and we came down. And this was the point. So this is theta equals 0, right there. And this is where theta was equal pi over 2, right? And then we went, and this is where theta was equal pi. And then we went on one more time like so, and this is where, so let's draw arrows here. Because with parametric curve, polar curve is not just a curve, it's a curve with a direction. So at this point, this is where theta was equal 3 pi over 2 or 2, and then we completed the deal, and we came back down here where theta was equal to pi. Okay? The point is, where do we see when r equals 0? Well, if you think about it, we start at 0, we went to pi over 2, halfway through will be pi over 4, right? And then we went from pi over 2 to pi, halfway through will be 3 pi over 4. Pi to 3 pi over 2, halfway through will be 5 pi over 4, and then from 3 pi over 2 to 2 pi halfway through will be 7 pi over 4. So we are going through r equals 0 basically 4 times. Okay? Another way to look at it is say, okay, I want at the pole r equals 0. Okay? This, since r equals cosine 2 theta, then this force cosine 2 theta to equal 0. This is 0. Okay, now, this happened when 2 theta equals either what? pi over 2, right? Or 3 pi over 2. But remember, theta goes from 0 to 2 pi. So 2 theta will go from 0 to 4 pi. So the next time, it will be 2 theta will be equals to 5 pi over 2, and finally 7 pi over 2. Okay, so theta equals pi over 4 divided by 2, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And we observe that result just by tracking the four-leaf rows. But if we start from 0 and we go to pi over 2, and then to pi, and then to 3 pi over 2, and then back to pi, we notice that every time we pass through 0, the angle will be either pi over 4, 3 pi over 4, 5 pi over 4, and so on. So you can obtain this result both analytically but also graphically if you trace the progression of theta, which when we did it last time, that's how we did it, if you remember. So what about the derivative here, the slope of the tangent? Well, dy d theta equals tangent theta, and we have two cases for pi over 4 and 5 pi over 4 in the first quadrant. In the second quadrant, we have, the first quadrant and third quadrant, the tangent is positive. So this will be 1, and in the second quadrant and the fourth quadrant, the tangent is negative. So it means that we have either slope of -1, slope equals 1, or -1. And the equation of the tangent are, if the slope is 1 or -1, because that's the value of the tangent, the y-intercept is 0 because we go through the origin. The pole is the origin. So we have y equals x, or y equals -x. Okay, let's sketch it again so you can see that this is correct. I'll try to sketch it at a little bit larger scale here. And this time I'm sketching it on the xy coordinate system. So okay, so this is a four-leaf rows, or four-petal rows, and you can see that the tangent at the origin, at the pole, this will be the line either theta equals pi over 4. Remember, we said that in a polar curve, in polar coordinate system, r equal to constant is a circle, and theta equal to constant is a line. So this is the line theta equals pi over 4, or in the xy in Cartesian system, it would be y equal x. And then the other tangent right here, you can see, is this one. And this line is theta equal, it would be 3 pi over 4, or y equals -x. Okay, so those are the tangents. Okay. What about the other values? 5 pi over 4, 7 pi over 4? Well, that's basically we are repeating the tangents. So pi over 4, or 5 pi over 4, and 3 pi over 4, 7 pi over 4 are the same line. So we might as well write pi over 4 or 5 pi over 4, that, and this one will be 3 pi over 4 or 7 pi over 4. Okay?